Okay, so I'm going to jump right in here to Remote Learning 6 Part 2, and we are going to be determining the solid obtained from rotating a particular bounded region here in green, but this time it's going to be around a rather arbitrary axis rather than the x or y axis themselves. Okay, so this is going to be revolved around the vertical line x equals 6, and the bounded region is a result of taking a look at this square root function and this line. Okay, so I might be referring to this one later as the so-called blue function, and then this is the red function. Okay, so just in terms of parent functions and translations, uh, this is the parent function root x, which generally just looks like this, and it's been shifted over to the right one and is twice as steep. So it's been shifted over to the right one and is steeper than normal. So there it is. And then this is the line. Okay, so this region is looped around the vertical line y equals x to obtain this solid over here, which is, I suppose, a solid, but it does have a big giant hole in it. You can see the silhouette going on. So we're looking at this amount of volume, but rotated around that vertical line. Okay, the cross section then is down below here, and you can see that there is one of many cylinders that you could draw within it. For instance, I could draw a cylinder down below here, and that cylinder would look something like this. And this cylinder would have a thickness and a radius, and a height, and we could find its volume. And the idea is that we just have like all sorts of these cylinders that we're finding the volumes of, and then we're adding up all of them. We're going to make them infinitely thin in terms of this delta here, and therefore we'll need infinitely many of them. And that's the idea of integral calculus, of course. We're adding together infinitely many things. Okay, so let me get rid of that mess and start talking about this particular ith cylinder. So I'm going to call this value down here x sub I. X sub I could be anywhere between 1 and 5. Those are some suitable places where I could slide my xi value and stop and create a cylinder. I can't create a cylinder over on this side or between 5 and 6, right? Because there's no volume there. The region's bounded by this. Okay, so why am I convinced that it's between 1 and 5 is because I can see that from the graph. But if we were to be a little more official about that, then we would equate these two functions and confirm that their intercepts are at x values 1 and 5. Okay, so I'll make quick work of this by squaring this side and squaring this side and bringing everything over here to the right hand side and factoring. Okay, so we can be convinced that our x values are 1 and 5. You can use the red function to see that the heights associated with 1 or 5 are 0 and 4. Okay, so enough of that sort of algebra 1 busy work. All right, let's get back into the calculus. So x1 is an arbitrary place where I've now located an arbitrary cylinder, but again, I could slide x1 anywhere between 1 and 5 and still come up with a viable cylinder. All right then, so the volume of the ith cylinder is dependent upon its circumference and its height and its thickness, which I think we've by now sort of done enough of. And we'll just go ahead and call that delta x, this little tiny thickness here. Okay, so the circumference. The circumference depends upon the radius, and the radius I'm drawing right now is this length. Being careful to draw it actually, you know, um, so that it moves from the axis of rotation to the xi value, and I'm being careful to make sure my xi value is actually between the bounded part of the function, not anywhere over here in the mirror. I'm not putting xi over here. These functions are not given, right? They're just the results of the rotation. So we want to just be considering this bounded region when we think through radiuses and heights and things. Okay, so then this length is, the dependent upon that point and that point. This point is over 6. So circumference, 2 pi radius, 2 pi 6 minus, and then I need to subtract off this length, which is the length xi. Okay, so then I have the circumference. Now the height is going to be a little more complicated. The height is here. So going with height. And the height depends upon the xi value, because the height will change as you slide the xi value. But at this particular xi value, the height is the height associated with the blue function minus the height associated with the red function. Okay, so these functions are heights equal and height equal, so it's such that we can just put in x sub i's and get the corresponding heights associated with them. Okay, so then the blue height is 2 root xi minus 1, and then we need to subtract from that the red height, careful with the parentheses, which is xi minus 1, and then that's all delta x. It's not quite dx yet. We haven't thought through the adding together infinitely many of them. That's just one cylinder's volume. Okay, so then we know that if you then add together n many such volumes together, you get the collection of all of the cylinders that make up the volume of the solid. Okay, or close to it anyway. As long as you run n to infinity, then you'll get the exact thing. And this is the notion that is the integral. Okay, so we used to run the trilogy right here, and now that we've done so many, we have our just a little shortcut that we've developed. Okay, so then that is the integral that represents the volume of the solid, and it's 2 pi, this Vollender cylinder formula, which is up above. So we've got 6 minus x times 2 root x minus 1 minus x plus 1 dx. And let's talk about the limits of integration. So that's back to the slider idea, and this slider can slide between 1 and 5. Okay, so then that's our integral, and I'm just going to rely on my calculator and go get that integral. And just give me 1 second to go do that. And that integral is 272 pi over 15. Okay, that 7 doesn't look totally obvious, so let's get that again. Now, if we want to talk about how we would do it by hand, well, it would be epically long, but it would be doable in the sense that we could distribute the 6 to everybody, distribute the negative x to everybody, get a string and break it into a bunch of different integrals. One of them would involve, this 12 root x minus 1. That'd be a u sub. There'd be some power rule, reverse power rules. That would be fine. This would be the tough one when negative x lands on this. So you essentially have after you plot the constant, you have like a x root x minus 1. And that is a u sub with a twist. That's like a u sub where you have to go and use the u sub and do a second substitution. So it would be tricky, but we did do problems like that. So it would just be tough. Okay, so I'm going to let this one go and go on to a new one where the cylinder is rotated 90 degrees. And instead of having dx's, we'll have dy's. And instead of having things in terms of x, it'll be in terms of y. Yeah, okay, so let's get into that one. And here it is. So again, this is the solid obtained by graphing the two functions. I'll talk more about that in a moment. And then that is going to be rotated around the line y equals -1 to obtain the solid, which is some cup-like looking solid with a garbage can shape taken out of it. So again, think about this as air, and then the volume is the stuff. Okay, so just more to these functions. The blue one is a sideways parabola that opens to the right, positive leading coefficient. It has a vertex at 0, 2. There it is. And this is a 1, so it's the standard 1, 1, 2, 4, down 1, right 1. Okay, and then that is y equals x line. Okay, so they've changed the scale a little bit here. And on this one, I'm not going to take the time to find where these points are, but they are at 1, 1, and 4, 4. Okay, so then here is our cross-section of some arbitrary cylinder, and this arbitrary cylinder is situated here at y sub I. So I'm using the height y sub I to talk about this particular cylinder. And this height could slide anywhere between 1, so I could have a cylinder that's here, and I could have a cylinder that's way up here, etc. But this y slider is going to be sliding between 1 and 4 only. Okay, so we'll think about that later on when we get to the limits of integration. Okay, so then let's get into calculating the volume of this particular cylinder, which I call the ith cylinder. So it has a circumference, which is 2 pi times its radius. Its radius is this length. Now this length is a little trickier though, because the center is off of this horizontal line -1, and so the distance is this top value minus this low value, the top value being y sub I, and then we need to subtract from that bottom value, the difference in their heights, right? So difference in the height of the one and height of the other is -1. I'll switch that to y plus 1 in a moment. Okay, so then that is the circumference, and then we need to multiply that by the height of the cylinder. Okay, the height of the cylinder, you're thinking height, you think it's going to go up, down, but the height of the cylinder, the way it's positioned, is this green one. Okay, so we need to know how far over it took us to get to that point, and we needed to know how far over it took us to get to that point, and that's contingent upon where the slider has stopped. Well, if our slider stops at y sub I, then we use the red function to go get that value. We want to know its x value, and its x value is its y value because it was the equation y equals x. Okay, so that is the overness associated with the red function when we're at height y sub I. Okay, then we're going to subtract from that. I always use parentheses, maybe even if I don't need them, because watch out for those minus signs. Okay, so now we need to know how far over we went when we were at height y sub I on the blue function. And that's exactly how this function is laid out. It's laid out so that it'll give us the x value when we put in some arbitrary height. So the x sub I value is y sub I minus 2 squared. And then we have delta y as the thickness. Delta y as the thickness, just making sure you're grabbing that. That thickness right there is a change in the y direction. That's delta y. Okay, so then we're almost to our integral. We just sort of want to just remind you always that we're going to add together n many of those cylinder volumes as n moves to infinity, and that is what creates the integral. Plucking out the constant, and it looks like I have left behind y plus 1 times the quantity. Oh, let's see, how much algebra am I going to do here? I'll do a little bit of algebra. So let's turn this into y squared minus 4y plus 4. Okay, so let's just, I'm not putting the sub i's on there. Okay, so let's see, we get negative y squared and negative 4y plus 1 more, that's negative 5y, and minus 4, and then dy, an infinitesimally small change in y. Okay, so this one would be easier to do by hand, but super tedious. Oh, and then limits of integration, yeah. Worth talking about. I somehow do tend to forget those. That's back to the slider idea. Okay, so where could these values be? They could be anywhere between 1 and 4. So 1 and 4. Okay, so then I'm going to hop to my calculator and get all of that. And that turns out to be 63 pi over 2. Okay, so I made quick work of those two problems considering their level of difficulty. And I have 2 for you to try and 1 for you to suffer through. No, sorry. But I do have a challenge problem. Okay, so then this is the assignment. These two are, let's see, so these are horizontal lines. And so they're rotating around that horizontal line, and then this one is rotated around a vertical line. Okay, thanks. Please hop into the meets. I'll be there to help you.